And yes. Okay. Now, anything you say from this moment on can be used to progress science, I suppose. Okay. Let me do the introduction. And we're very happy that Jurriaan, Jur for short, is here to present a talk on a pro and con of static typing. He did his studies and his PhD in Leiden on the topic of combinatorics and algorithmics of graph and group theory. He moved to Utrecht in 2000 and he changed his field of research to static analysis of programming languages. It's a very hot area, actually. There are a lot of new programming languages, new tools coming up, so it's a very rich field. His work is mostly on functional programming languages and in the areas of higher order type systems, type error diagnosis, and optimization. And in addition, he leads the maintenance of the Helium Haskell compiler that was initiated in Utrecht. He also applies static analysis to languages in other paradigms, for example, program plagiarism detection for C# and type analysis for PHP. In his spare time, he collects music, produces music documentaries, and writes about music. And during the pandemic, he spends a lot of his time apparently in the gym. Okay. Jurriaan, the floor is yours. I'll mute my microphone and camera.
All right. Let me see if I can share. It's a bit slow here. All right. Come on.
Can
you see it?
Yes.
Okay. Okay. So, yeah, welcome to my presentation, a pro and con of static typing. So in the original abstract, I think I had 2 pros and 2 cons and 1 pro, but it turned out there was not enough time for both cons. So this is what we'll just have to settle for. So basically there are 3 parts here. First, I'll explain what are type systems and what are they good for. The first, then I will discuss a con, a disadvantage maybe of having a type system is that you sometimes need to fight it. I'll give you an example and also discuss a paper that we've written to help fight the type system. Then there's kind of like an unexpected advantage to having a type system, and that is that you can also use them to do optimization, not just for validation. I was also planning to do some type error diagnosis, but I decided against it, maybe for another time. So first, what are type systems and what are they good for? So at its simplest, what is a type? It's basically a set of values. So usually if you've programmed, you typically have some of these in mind. You have the integers, you have floats, list of floats, maybe sets of strings, references to some class, what have you. Depends, of course, intimately on the programming language. Now, usually operations in a programming language are defined uniformly over values of a certain type. So for example, if I have the logical AND, it will work for Booleans, but not for values of other types like strings. Now, a type system tells you when operations could be applied to values they were not defined for. So you write something in your program, and then a type system will tell you, no, this is maybe wrong because you're passing a value of an incorrect type to an operation. So for example, in Haskell, you can say true and false, which of course will be false, but you cannot say true and the string hello because hello does not have the right type. It's not a Boolean. Now, this is in Haskell, but every programming language makes its own choices. For example, in PHP, almost everything is well defined. There are hardly any errors that you can make. Of course, you can still make mistakes in the sense that the program will not do what you want it to do, but it's not a type error. Now, if we talk about choices and the programming choices that programming languages make, at a very high level, they make 2 choices. They either go for static or dynamic checking, and they tend to go for a strong versus a weak type system. Let's first look at static versus dynamic. So static means that you check all your types before ever running the program. So for example, Haskell and C# are languages in our bachelor that have that property. It basically means if your program is type correct, you cannot even run it because it will not, no code will be generated. Other languages are dynamic, and there the type checking is performed during running. So for example, Scheme is an example of a functional programming language that doesn't do static type checking, and Python is an example of a object-oriented language that has. And in the end, yeah, if we talk about realistic programming language in real life, then most programming languages are somewhere in between static and dynamic. Some of them are checked maybe beforehand, some of them are maybe checked during runtime. There's also the distinction between strong and weak. So in a strongly typed language, you have a large variety of types. So you have a very refined type universe. Haskell, Scala, and Agda are examples of such languages. But Java and C# are also not that bad. Not as strong as these languages, but still quite strong. If we talk about really weak languages, then we have PHP, where basically everything is compatible with everything else, almost. Now, the idea is that a static type system catches mistakes soon, because it will catch them at compile time, not at runtime. And strong type systems give you more errors. Of course, if you never make a mistake, then the distinction is maybe not that interesting because nobody will get hurt. However, it does start to hurt when you do software construction and maintenance in a situation where you have multiple teams working at multiple locations over multiple years using multiple language technologies, where you have people coming and going, people forgetting invariants, people leaving with their invariants and nobody knows what they are. And if you have a system that is actually in use, it has to adapt to the world around it. So it will always be evolving and changing. And types are, in fact, a very good way to keep at least some kind of confidence that if you make a change, and then at least maybe the types when you compile it are known to be correct. There's also companies who've realized this. Marktplaats, for example, moved from PHP to Scala. Microsoft moved from JavaScript to TypeScript, or developed TypeScript as an answer to the problems they had with JavaScript. And Facebook did something similar, where they took PHP and transformed it into Hage. So what do statically enforced types give you? Well, they give you, like I said, guarantees at every time you compile, but they are only primary care, or what we call in the Netherlands, eerste lijnzorg. So it's fast, and it catches a lot of mistakes, but it will not typically catch all your mistakes. But because it's fast, that's okay. If there are still properties that you cannot really guarantee with your types, you can still write tests, you can still prove your program correct, or you can still apply model checking. Another reason why it's good to have types is that they serve as documentation. So this is the typical map function that takes a list of A's, and I can apply a function from A to B, and then by applying that function to every element in my list of A's, I get a list of B's. And that's the idea of a map. This A and B can be anything. So A could be an integer and B could be a float, and then it takes a list of ints to a list of floats, and so on. This is called a polymorphic type, in case you've never seen one. So how do you define a statically typed language? Well, basically, if you define a programming language, you have a semantics in mind, you have a syntax, you have your lexical items. In this case, you also define a sound type system. So this is a specification of when is a program type correct and when is it not. And this should be consistent with the semantics. That's what I mean with the word sound. There should also be implementation of the type system. And typically this is part of the compiler. The compiler will check at every compilation that all the types are okay. Now, how do you formulate such a type system? Well, typically we do this in the form of a set of logical deduction rules. I have one rule typically for each language construct. So here we have the language construct, the conditional if then else. So this is a construct that says, well, the keyword if followed by some expression T1, followed by then, followed by the expression T2, followed by else, followed by T3, has the type tau if I can prove that T1 is something of type bool, because I need to distinguish based on a Boolean value, true or false. T2 has the same type tau as what I deliver in the end, and T3 also has that same type tau. So essentially what the conditional rule basically enforces is that one, the condition has type bool, and the then and the else part have to have compatible types, the same type in fact. Okay, so with this under our belt, let's look at why you sometimes need to fight the type system. We talked about soundness, and why you need to fight the type system is because type systems are not complete. If we look at the Rice's theorem, this is a basic theorem in computability theory. In any sufficiently powerful programming language, every non-trivial property of the behavior of a program is undecidable. So you cannot have completeness unless you give up soundness. But soundness means we cannot trust the compiler anymore. So we prefer to trust the compiler and give up completeness. The bad news is there will always be programs that go right, that won't crash or fail or whatever, but they are still considered wrong by any given type, by a given type system. There's good news too. If you observe this happening, you can, for that particular program, refine the type system to accept it, or a whole class of its programs. Let's look at an example in Haskell. So here we have the identity function. It's a function that takes a value of type A to a value of type A. The only thing it does, it gets an input and it gives it back as the output. Very stupid function, but we often use it in Haskell. I've defined it in a rather strange way. I've defined the identity function by applying the identity function to the identity function. But if I apply the identity function to an identity function, I get the identity function back. So this is maybe strange to write it like this, but we'll see in a minute why I did it like that. So this program is type correct. It has the type A to A. Actually, it has the type for all A to A, but we always omit the for all in these types over here. And it will indeed not generate, it will execute without crashing. How can you tell? Well, you can, for example, look at the application of this function lambda y to y to this other function lambda y to y. This is the application rule, exactly like we had the if then else conditional rule earlier on. This is an application rule that says if I have an application in my program, then I first verify that the first part is a function and the second part is an argument that fits the function. And then the result of the entire application is the result of this function. In this case, when I choose tau1 and tau2 to be A to A, it will all fit magically together. And this is what an algorithm will actually even infer for us. Even if we don't tell it what the types are, it can infer this type. And note that both these types, that if we choose tau1 and tau2 to have these types, that T1 is actually of the type for A to A to A to A, and that T2 has type A to A. Both of these, and this will be important in a minute, are different instances of the same polymorphic type for all B to B. Now, what if we write this same function in a different way? This is basically the same function. It will more or less execute with one additional step in the same way. But now I have the identity function here, the one that I had here on the previous slide. But now I have another function that will execute pass this x to itself, which is basically the same as what I did here. This doesn't type check, but it would not crash if we could run it, which we can't because Haskell will not generate any code if it doesn't type check. And you get a message like this, cannot construct the infinite type. So type correctness depends on how we write our program. What's the problem? Well, the problem is that here we needed two different types for our lambda y to y. One of the lambda y to y's was A to A to A to A, and the other y to y was A to A. But here, because of this lambda, we have to commit to one choice and one choice only as an instance. And these can never be mutually compatible. Well, this pissed a lot of people off when they found this out. So type theory said, we can solve this, we invent higher rank types. And in fact, if you look in the de facto standard Haskell compiler, GHC, it actually already has an extension and support for it. How does it help? Well, basically it means that you have to give explicit information about the type of X to GHC, and it can then verify that this is consistent. So you have to tell the compiler in one way or another, look, this X here has to be an instance of the type for all B to B, and this will allow us to make different instances for the separate X's, and it will also allow us to verify that what we pass into the function is actually of the right form. But we don't get something for nothing. This will now type check with this extension on, but we don't get something for nothing because full inference goes out of the window. If I write a program without any types, it can still type it. But now it goes out of the window because actually type inference for higher rank types is known to be undecided. Type errors may also suffer, but we still want these higher rank types because workarounds are difficult. I will not give any examples. So this is my basic introduction. So this is basically material that our master students more or less will know. And now I want to go over to my research contribution, but I'll try to skim on the details, the technical details. So how did our research start in this arena? Back in 2014, I was with Alejandro, and we wanted to look at GHC's design for higher rank types because we wanted to improve the error diagnosis. We came up with a new notion called guardedness. I'll give some details in a minute. And what was nice about it, it actually also gave us a handle on what is a more complicated notion, more complicated than higher rank types, namely that of impredicativity. Now, we got into contact with Simon Peyton-Jones and Dimitrios Vitaniotis, the lead maintainers of GHC at Microsoft Research, who had tried to add impredicativity to GHC for a few times, but had failed twice. In the end, we came up with a redesign of Haskell's type system to include not only higher rank types, but also impredicative types. Now, this idea of guardedness is basically, and I'm going to skip the technical details a bit more, but the idea is to take advantage of a very common situation where, so in the usual case, the problem of higher rank is that there are moments where you need to choose between instantiating or not. And this problem, and also what you instantiate with. And we kind of identified a large class of situations where there is actually no choice. So you know that if there is a choice that will make it work, it has to be this one. And then we try to make the most of this information by propagating that information as much as possible throughout the program. This is the basic idea. Now, technical details are way beyond what I can discuss right now, but what we can look at are the boundary conditions for this kind of research. So what do we take into account while we are doing this basically technical research? Well, there's a basic tenet, and this actually helps us, is that higher rank types are never guessed. So a higher rank type, whenever a variable has a higher rank type, it can only be because the programmer in one way or another communicated this to us. And the challenge is just to make the most of what is given. Now, there were a few boundary conditions, like I said before. First of all, we need to be able to give a declarative specification. Declarative means it should be independent on how the compiler uses a type system. It should only be based on the specification of the type system, because a programmer doesn't know how internally a compiler does its work. There are actually two kinds of specification: a set of logical deduction rules, like we saw before, that we have to prove sound, of course, but also some kind of intuitive, explainable manual style explanation to be used by actual programmers. The complication here, and this is specifically with impredicativity, it's very tempting to take advantage of how you do things. So you should always try to avoid that. It should also be easy to implement. I mean, GHC, the compiler, is a beast. It has a large number of other type system extensions where you can have all kinds of interactions. And in our final version in the compiler, we only needed 450 new lines of code in a 90,000 line type inference engine. So this is not the entire compiler. This is just the type inference engine. It also rids GHC, by the way, of a very special ugly Hage. It should also be, because there's lots of competition. So MLF, HMF, FPH, HML are works by other people who have also devised a type system to solve our problem that we also wanted to solve. And here the marks tell you, well, the no means that we cannot type correct. We cannot prove this program to be type correct, and the others can. And so this is a plus for them. And with some other programs, this can be the other way around, but you want to have as few no's as possible. We also did a lot of experiments because we take advantage of a simplification to Haskell. We did an experiment where we compiled 457 relevant packages and their dependencies to see whether the simplification would destroy the type correctness of the program. It turned out that in 97% of the cases, it's either just compiled or it was easy to modify because the compiler basically told you which expression to change. Another thing we looked at is if we have this new feature of impredicativity, can we, for example, remove all kinds of existing that uses a trick to kind of simulate impredicativity? And we found that in 6 of the 9 cases, we could actually do this. We also had to prove meta theory, most importantly, to prove our type system sound so that it could be trusted. But there's other things besides. Oops. For example, if we have a program like this, where zy equals first applying G to Y and then applying F to the result. Or in other words, Z is the function composition of F and G. I can also write it in Haskell in a different way. And if you're not careful, it may be that this program is accepted by the type checker, but this program may not. This is not something that we like. So what did this all lead to? Well, first of all, we wrote papers that included formal specification, an algorithm, meta theory, and a production quality implementation, and we did experiments. So we wrote 2 papers, one in 2018 and one in 2020. And these are really sizable papers. So this is 2 column style, 25 pages and 34 pages. And we were also very happy to receive a most distinguished paper at icsc. What's, I think, even more nicer, I think, at least for me, is that what we have done will also be part of the GHC actual release 9.2 that will probably take place next year. How long did this all take? Well, Simon Page-Jones said he started 15 years ago, and he tried it twice and barely escaped with his life. I think 2.5 years ago, 3.5 years ago, 4.5 years ago, we got into contact with them. It took us 3.5 paper, including 2 visits to Cambridge, and then the final paper took about a year. Now I'd like to admit, no idea how I was for time.
You have 10 more minutes, so you're
Good.
Quite comfortable.
Yeah, I'm quite comfortable. All right, so this was our, let's say maybe my first trip into type system design, because actually what I intended to do was to work on type error diagnosis for hiring types. We never got around to that. Alejandro got his PhD. This was in it, very nice, but I still need to work on the type errors for hiring types and imperativity, and I hope to do that with in the future. But now I want to move to a different topic, and this is type-based optimization. I'll keep it very informal. If you think this is interesting, a large part of the course I teach at my master level, Info MAPA, actually discusses this in some detail. So what's the idea? Well, let's look at the compiler first. So a compiler consists of a front end and a back end, not a front end, but a front end. So in the front end, you parse the program and you type, and then you go to the back end. Then you know that the program is type correct, because otherwise you will never end up in the backend. You desugar the program to some simplified form, and then you start analyzing the program for optimization opportunities. In particular, for functional languages, because they are so high level, you need to do a lot of analysis to be able to generate competitive code. And then you can use the analysis information to generate efficient code. Now, what if we are in a situation that we are working with a programming language that has a static type system? Well, Lucassen and Gifford had an excellent idea. Back in 1988, they proved that you can use a variant of a type system to formulate an optimizing analysis. These are called annotated type systems, and other people will call them non-standard type systems, and other people will call them type and effect systems. Doesn't really matter. The essence of the idea is that you attach analysis information to your types, and you infer that information along with the types as you're doing the type checking. One particularly interesting aspect of this is that you already have an implementation of a type system in your compiler. So now it's just a slightly more complicated, maybe, implementation of that algorithm in your compiler, but it's not very different. You can reuse all kinds of concepts like polymorphism from the type level. You can also reuse them in this setting. You get all kinds of vocabulary and proof techniques. You can all reuse them from static type systems to do your optimizations. So make that a bit more concrete. So how do you specify such an analysis? Well, basically the same way as we did before with the if rule and the application rule. So an analysis is formulated as a set of logical deduction rules, but our types are now slightly different. Instead of just having types like int and function from A to B, we annotate our types with elements from a complete lattice. It's not that complicated, not that important if you know that what they are. But for example, if you look at the sign analysis, we want to, for example, distinguish between variables of type integer that are always negative or always 0, or maybe that are always 0 or positive, and so However, we can typically use that kind of information to generate better code. So in this case, our complete lattice is the set of all subsets of -0 plus. So if you talk about a value like 1, so you have the value 1 in your program, it has type int, clearly, but it has an annotated type int, where I put the annotation, the set with plus, in a superscript. So this means not just it's an int, but I even know that 1 is a positive int. Now, annotated types systems never fail to analyze. So where a static type system can actually fail because your program is not type correct, optimization should always be okay. You may not be allowed to make the optimization, but you should never say to the programmer, can't optimize. So what they do is, instead of failing, they approximate. For example, if I have the value 1, it's also okay to say that this is an integer that may be positive or negative. Of course, I know it's never negative, but I can still say this. And then, in this research that addresses this field, you're going to play the precision game. So there's lots of complicated words here, but essentially what you're doing, there are lots of choices in which you can tailor the precision of your analysis. And for example, I'll give you an example about annotation polymorphism. So here we have a function it for ints, that is the identity function that only works for integers. What type should we give it? Well, if you give it a positive integer, of course, it's going to give back a positive integer. But the problem is now I cannot pass a negative integer to it for ints because it doesn't have a story for that. So maybe I should give it this type. You can give me any integer and I give you any integer back. But now if I pass in a negative integer, out comes an integer for which I know nothing anymore. This is very bad. So now we're going to add polymorphism to our annotated types. We're going to say, but the best type for this kind of function is, if you give me an integer with some property beta, I give you back an integer with that same property beta. As a maybe an aside, at ISFP 2010, we had a paper where we showed that full inference of higher ranked annotation polymorphism. So this is plain annotation polymorphism, but now higher ranked, like I discussed in the first part of my talk, is actually decidable, which is very surprising. If you want to know, do you actually apply these kinds of analyses? Well, actually, we have some of these implemented in our own Helium compiler. So to conclude, I gave you a short tour of the world of type systems for functional languages. I tried to at least give you some insight at a very high level into type system design and type-based optimization. There, of course, are 2 papers about type system design that you can probably find, but if you want, I can send them to you. If you want to know more about type-based optimization, I can teach a course where this takes place. And like I said before, type error diagnosis will have to wait for another opportunity. These are people I've collaborated with for the topics I've discussed in this particular talk, and now I'm ready to take your questions. Thank you.
Thank you very much. First, a round of applause, maybe. Okay, we're ready to take questions. I see no questions in the chat window, but you can raise your hands to ask a question. And while you do that, let me ask a first short question. In the last, well, the penultimate slide, you've shown this parameterized form where a property beta can be guaranteed to be in the domain as well. Are there any constraints on how we can specify beta? Can I define those, or are there families of constraints which work well and families which are problematic to implement?
Well, I mean, so constraints that we allow in to impose. So you might, for example, have for all beta 1, beta 2, and then have some restriction on beta 1 and beta 2. I think this is more or less what you hint at, right?
For instance, can I choose beta to be prime numbers? I don't know. I mean,
no.
Constraints could be quite different.
It doesn't work like that. So first of all, these betas will. So beta ranges over the complete lattice that you chose. And basically, the only operation disposal is basically, well, you have to join the meets and the partial ordering on which the complete lattice is based. These are the kinds of operators you can use in your constraints.
Mhm.
But it's still the case that some of, sometimes, so typically what we want is that we only use this partial order relationship to express everything. That makes our life certainly easier. So there's actually quite a lot of complications that you get into, and also in terms of performance, and also in terms of decidability, that you really have to take care of. But generally, if you take a complete lattice, and the constraints that you impose are all what we call, in this case, for example, in the sign analysis, this set is smaller than that set, or at least as large as this other set, then you're fine.
Okay. Any further questions? Yes, Mark.
Yeah, you talked about optimizing your code, right? To be competitive with other code, I guess.
Yes.
Is this always done in an experimental way in your field of research, or is there also a formal way to analyze how well optimization has happened?
Yeah, actually, you might say there are sort of two ways. I mean, in the end, if you talk about how well are we doing on realistic programs, this is always a benchmark issue.
Of course.
So like, no fit benchmark, and there's a number of these benchmarks. For example, GHC itself comes with a large number of benchmarks, so they can kind of keep track of how they're doing in terms of computation time. However, when I talked about earlier these notions like annotation, polymorphism, subtyping, this kind of gives you a hierarchy. So, for example, subtyping is more powerful than subaffecting. So you can kind of say, well, if you define a static analysis and you can say, well, look, my static analysis has subtyping and it has annotation polymorphism, and this is more or less state of the art, then you're already as good, more or less, as you can be. And for other static analysts, this will about how powerful your analysis is. It still doesn't mean that having more precision is going to help you on realistic programs, right? But I do know, so for example, I do know that in GHC, for example, so this compiler I talked to you earlier, they have static analyses, but some of these static analyses are they're very first order, so they're very plain, low precision. And the reason why they chose is because of speed, because doing a very precise analysis also takes a lot of time, can take a lot of time. So, and because they're an industry standard compiler, and this is bad for them because people use GHC to compile really big programs. And they say, well, because we do all kinds of previous optimizations that will already kind of make our programs of a form that it's not too bad for us to implement our static analyses in a very simple way. Yeah, they thought they could get away with that. Although they did an analysis afterwards, and there they found that still there are large classes of programs where they know by looking at the program we should be able to generate better code, but given our choice for the precision of our analysis, this is not going to work. Yeah. So So the short is, if you look at the properties of your analysis, you can typically see this one is better than that one. But in the end, it's always the benchmarks that kind of have to tell you, well, realistically, what does this tell? What's used for the real programmer?
Okay, thank you.
So the analysis is typically done by analyzing programs themselves, not this process of programming. Like, for instance, are there repositories where you can look at errors during the compilation made by the programmers, or?
But now you mean type errors again, right?
For example.
Yes, because this latter part will never give you a type error. It will always do. It may not optimize as much as you want, but it will not fail. The type system can fail with a type error, and actually, it's one of the biggest problems in the field of type error diagnosis is the absence of benchmarks. So I made one in 2005, but this was still for pretty plain Haskell. So these were programs written by our students in their second year functional programming course, and I collected these. And and other people have used these programs. Other researchers have also used these programs that I anonymized, of course, before I gave them to them. But this is not something that is easily available. And this is a major problem, at least for my field of type error diagnosis. Yeah.
Okay. We have two more questions. First, Frank, and then Hugo. Frank, please.
Yeah. So is there a sort of a notion of approximation ratio or something like this for optimization? So, I mean, can I know if I'm done?
No, I don't think so. I mean, there are probably certain classes where you can know that you are done. So, for example, if you make your functions more higher order, and you know what that means, then at some point you're going to lose precision if you don't have subtyping. Even if you have subtyping and an annotation polymorphism, for example. But in the end, no, I don't think I've seen anybody ever doing anything that's even close to putting a number on how close you are to the best result. I mean, the thing is that we always get best results when we do our static analysis. We always get best results. The problem is that the approximation is in the equations we generate, and there's a lot of choices you can make there. For example, most static analyses are not path sensitive, so they are not. They don't try to kind of, if you have an if then else, push different properties into the then part from the else part. Why not? Because it blows up incredibly. And you can always write programs that where you would profit from this kind of information. But because in general, this kind of information blows up, and in fact, it will quickly become undecidable. Yeah, this is kind of like, yeah. That's why it doesn't really make sense to then continue.
Frank, does that answer the question?
Yeah, I think so. Well, yeah, I guess so.
Okay, Hugo, please.
I was wondering if the technique you described can also be translated to compilers for imperative languages, or does the problem not even arise in that class of language?
Well, certainly. I mean, so imperative. So first of all, I mean, this is if you talked about the type-based analysis, or you talk about the higher rankness.
The higher rankness.
Okay, yeah. So there it doesn't show up because, I mean, well, if you have a type system that has higher rank types, then they have the same problem. Of course, the boundary conditions in their setting will be completely different. So it may well be that you have to you will make completely different choices. For example, if you take Scala, Scala's basic type system is already quite a bit more, even the basic type system is already quite a bit more complicated than the basic type system of Haskell, which is Damas-Milner. So I'm not aware of people at Scala doing higher ranked or imperative types. I don't know. I do know that, for example, in ML, they do it, but ML is very much like Haskell anyway. So that's not so strange. But Scala, for example, is a much more complicated language because they have a special algorithm called local type inferencing, which by itself is already difficult to get right, let alone if you add all these new features. But I think they can still take inspiration because the basic idea of our analysis is to take advantage of a particular class of in the case of Scala, then method invocations, where you don't have a choice, but you can kind of say, well, it has to be this, and I will continue using that information from now on. Yeah, that basic idea will still apply. That I'm pretty sure about. But it's also the case that during our analysis, during the work we did for this imperative and higher rank types, I mean, we spent 3.5 years going from one version to the other version, and then backing up when it turned out we were either accepting too much or too little, or when we were we thought, well, now we have a system that actually does all the examples we want to be able to accept, but we have no way of explaining this to a programmer anymore. The system has become too complicated. So this is kind of like, yeah, we kind of like rats in a maze and continually bumping your head. And that's also why it takes so long, because every time you have a new idea, you have to build it into the compiler, see if it works, and then try some programs. And then you start to prove the meta theory. And sometimes we had good ideas, but we never could get the meta theory proven, for example. Then you have to back up again. But yeah, in answer to your question, yes, I think in Scala they could also do it. I don't think, for example, Haskell, now Java, C#, their type system is a bit too distinct, I think, from the type system that Haskell has. That would be easy enough, or that would actually make sense. In Scala would make sense because it is by design a very higher order language.
All right, thank you.
Let's take the last question from Vishnu.
Hi.
Hi.
Yeah, so I have a simple question. So the beta annotation that you have in, I think, one of the last slides, is that something that programmer has to write, or is it something that your system can infer?
No, actually, the programmer never sees any of these annotations. This is all in the backend only.
Okay, thank you.
Yeah. Thanks for pointing that out.
Well, this has been a very lively discussion. Thank you very much. Thanks for all the contributors, and see you next week. Thank you very much. One final round of applause for our speaker, please.
Thank you.